All right, this is our last topic. So we're going to take a look at the law of cosines. The law of cosines is essentially going to help us solve those two cases that our law of sines messed up on or couldn't do. Remember the SAS case? If I draw it, looked something like this, where we have a side length and an angle and a side length. And the problem was what we didn't have this connection between an angle and its opposite side length, right? In all three of these, we're missing a piece, whether we're missing the side length over here that we don't know, or an angle here that we don't know, or an angle here that we don't know. And our other one, the SSS case, is clearly we don't have any pairs because we don't have any of the angles. We have no idea what's going on in here, so we can't make any sort of connections again. If we had all angles, then all you would know is that the triangle was going to be similar to other triangles and stuff like that. And so that ends up being a tricky one as well. It's really impossible to nail down what the side lengths are. So we really don't look at the AAA case because it's can be anything. Anyways, this is the law of cosines. This is going to help us out. I'm not going to derive it in this, but you will recognize some stuff. So let me just read this off, and then you can kind of see what's going on. If capital A, B, and C are the measures of the angles of a triangle, and lowercase a, b, and c are the lengths of the opposite sides, just like normal, then we've got this totally recognizable setup, especially that third one. A squared plus B squared, and there's a C squared on the other side. We just have this extra offsetting term, but this looks like the Pythagorean identity. Oh boy, I can't type right now. Or maybe I'll say the Pythagorean Theorem. Now, the Pythagorean Theorem works for right angle triangles. So what I want to do is take a look at this third one and say, what if C was equal to 90 degrees, or pi over 2 radians? Well, then C squared would equal a squared plus b squared minus 2ab cosine of pi over 2. And cosine of pi over 2 is 0. So c squared equals a squared plus b squared. So the Pythagorean theorem is just the law of cosines when the angle here is 90 degrees, or pi over 2 when we have a right angle. So this is like a more general version of the Pythagorean theorem. It's a really interesting thing. It works for non-right triangles, so any angles, but it'll also work for a right triangle as well. You just drop into the Pythagorean theorem. This is going to be really helpful. We're only going to use the law of cosines when we absolutely have to. In general, people kind of agree that it's easier to use the law of sines overall, and so whenever we can use the law of sines, I'll refer back to that. So we're going to use the law of cosines to get out of this jam, where we have these two triangles and we don't really know what's happening. Notice in this first one with the green stuff, once we get one of these angles or side length, we've got a pair of angle and side length that's opposite that we can use the law of sines to do. And same thing here. Once we get one of these three angles, doesn't matter what they are, once we get one of them, then we have a pair of opposite angles and side lengths. So we'll use the law of cosines to get out of this sticking point here. So I'm just going to do an example of each of the cases that we have, the SAS case first, side, angle, side, and the SSS case second, side, side, side. So side, angle, side. So notice we've got an angle. We do not have the opposite side. We've got the other two, and we want to solve the triangle. I'm going to just break this down into some steps. So first, we're going to find A, lowercase a, side length A, using the law of cosines. So I might go back to my law of cosines, and I'm going to use this one. Notice I've got B, C, and capital A. So I'm going to go back, and I'll plug everything in for this. So A is equal to 7 squared, B squared, plus 8 squared, C squared, minus 2BC, so that's 2 times 7 times 8, times cosine of capital A, 120 degrees. Let me just write this out. This is 49 plus 64. 49 plus 64 is 113, minus 2 times 7 times 8. 7 times 8 is 56, so 2 times that is 112, times cosine of 120 degrees. So let me grab a calculator and we'll say 113 minus 112 cosine of 120. And make sure that I'm in degree mode. And I've got that this is, oops, I forgot a squared here. My bad. So I've got that a squared is 169. This is the squared side length, so you could say a is really plus or minus the square root of 169, and isn't that 13? I'm pretty sure square root of 169 is 13. Yeah. Now, it doesn't make sense to think about the negative here, so we're just going to say a is equal to 13. Cool. We've got our side length. So I'm going to write that here. A is 13. And now we have an angle and opposite side length. We can find angle B or C, doesn't really matter, using the law of sines. So I'll just do B because that's the next one that we've got. Sine of B over 7 equals sine of 120 degrees over 13. And so I know that sine of B is going to be 7 sine of 120 degrees over 13. And then I can find out what B is by doing the inverse sine of all that stuff. So let me just write that out. Inverse sine of 7 sine 120 degrees over 13. That's going to give me 27.8 degrees. All right, and then I just know something right off the bat. My other option for this angle is 180 minus that. But I'm only allowed 60 more degrees in this triangle. This is clearly going to be bigger than 60, so that's not going to work. That's too big. So we only have the one triangle here. So our side length A is 13. Our angle B is 27.8. So let me write that here. A was 13. B is approximately 27.8 degrees. And then we can find the last angle. You could use the law of sines if you want, but why would we? Because we know that all the angles add up to 180. So I know that angle C is going to be 180 degrees minus 120 degrees minus 27.8 degrees. That's going to give me 32.2 degrees, I think. 180 minus 120 is 60. 60 minus 27.8 is 32.2. So I've got everything I need. Oops. Not too bad. Remember, we just used the law of cosines here, and once we had the law of cosines to get that last missing side length, we can just run through this and find angles. Finding those angles is pretty easy using the law of sines, and then just the fact that they all add up to 180 degrees. Not too bad. Notice you still can get stuck with this possibility of two triangles here. We use the law of sines to find that angle B, and if angle A wasn't as big and angle B was a little bit bigger, then the other possibility for it may have made sense. It might have been something that could have happened, and so you still can get two triangles this way, depending on what information you're given. So keep an eye out for that. That's not as normal. Mostly we see the ambiguous case when we have a law of sines set up, but you could have something like that. SSS. So we've got three side lengths here. So we're going to pretty much do the same order. We're going to use the law of cosines, then we're going to use the law of sines, then we're going to find the last angle. But now instead of using the law of cosines to find a side length, we have all the side length. So what we're going to do is we're going to find angle B using the law of cosines. A lot of places suggest to just do the biggest angle here. That way you don't run into any weird ambiguity things and stuff like that. It kind of doesn't really matter, but we'll do the biggest one. So I know this is going to be the biggest angle because lowercase b is the biggest side length. So that's how I knew that. So now I'm going to use the one solving for b squared in that law of cosines when I go up here, because now I'm looking for getting cosine b by itself, actually, so I can find angle b. So I'm going to use this version in that example. Where am I at here? Okay, cool. So I've got, maybe I'll write it out, b squared equals a squared plus c squared minus 2ac cosine b. So b squared is going to be 100. A squared is going to be 64. C squared is going to be 25. minus 2 times 8. I'll write this all out because I'm going to have a hard time keeping track of it in my head. Cosine b. So that's 80. So 100 equals 64 plus 25 is 89 minus 80. So that's 9. Oops, no, I can't do that. Sorry. 64 plus 25. Sorry, that's 89 minus 80 cosine b. So now I've got 100 minus 89 if I subtract both sides here. So that's going to be 11 equals negative 80 cosine b. And so all this to say cosine b equals negative 11 over 80. So this one's kind of a pain to get to. And now you can use the cosine inverse function. So we'll say, all right, cosine inverse of negative 11 over 80. That's going to give us 97.8 degrees. Now notice we don't have weird second angle stuff because cosine tells us an angle in the tells us an angle, or cosine inverse, tells us both of these angles here. So the ambiguity would come in this place. We have this angle available to us. Our cosine inverse spits out all of these, and we know that all of our angles are going to have to fit in there because that's our 0 to 180. We obviously can't have an angle bigger than that. So the other angle would be some negative one or something that's obviously too big, and so we don't have to worry about that. So that's really nice. So 97.8 degrees, that's our angle. So you don't have to do the biggest one first, but for whatever reason, that's what a couple places suggest. So what was that? Cosine, or B is 97.8 degrees. Let me write that here. And now we've got an angle. So that's B. So we can connect that here and then go from there. Okay. Yeah, I'm remembering why we do the big angle first. Because now we're going to find smaller angles with the law of sines, and we're going to have a better chance of not having weird ambiguity stuff. So you'll see how that goes. If you wanted, you could use the law of cosines still to find all these other angles. So you don't have to do this. Maybe I'll write this here. You can use cosines. It's just an annoying trade-off. The law of cosines is like a little bit more computationally annoying to do. You could say c squared equals a squared plus b squared minus 2ab cosine c and solve for cosine c and use the cosine inverse to get that. That's fine. I like using the law of sines because it's easy to remember, it's easy to set up, all that kind of stuff. You're going to get these formulas anyway, so if you'd rather use the law of cosines, that's okay. But it's pretty typical that people stick away from it. Anyways, so let's find, I don't know, do you want to find angle A? Let's do that. So I know that sine A over 8 is equal to sine of 97.8 degrees over 10. So I know that sine A is going to be 8 sine of 97.8 degrees over 10. And so A is going to be sine inverse of all that stuff. Let me grab my calculator. Sine inverse of 8 times sine of 97.8 degrees divided by 10. That's giving me 52.4 degrees. I think I want to go back here. Oh, no. We're good. Sorry. I got all in my head. Anyways, our secondary angle here, then you'll notice, is, what is that, 127.6 degrees. That adds up to 180. But notice, that's not going to work. So that's why we find the big angle, because then we can throw out this option when we need to. So I'll just say, nope, not a possibility. So we've got our other angle, 52.4 degrees. So it's 97.8 and 52.4. And then it's pretty easy to find the last angle because we know that C is going to be 180 minus 97.8 degrees minus 52.4 degrees. I'm just going to run through that real quick. So 180 minus 97.8 minus 52.4. Oops. There we go. 29.8 degrees. That looks about right. So there we go. We've got our three angles that we need. So the law of cosines is really helpful because it can get us out of those jams. Some people really like the law of cosines, and so they'll just use it for all the rest of these angles, or at least the one other one. So you don't have to use the law of sines to get that angle A in this case. And that's similar to our other example here. You don't have to use the law of sines to get this one here because you're going to use there it is, that side length A with the opposite here. Or sorry, you could use the side length A, B, and C with cosine B here. So you could say 7 squared equals 13 squared plus 8 squared minus blah, 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 blah. So you can use the law of cosines on that second one. That's all right. But we typically only use the law of cosines when we have to. Some people really like using it. You could also think of it this way. You could also say maybe it's better to use the law of cosines here because we still know all of these values, right? So maybe it is helpful to use the law of cosines. Let's just do that real quick and see. Because these 8, 10, and 5 values are fixed. So if we want to find this other angle, which I used A, I could say A squared equals B squared plus C squared minus 2BC cosine A. And we'll just do the same process that we did earlier. 64 equals 100 plus 25 minus 2 times 10 times 5. That's 10 times 10, so that's 100 cosine A. 64 minus 125, what's that going to be? So I've got negative 61 equals negative 100 cosine A. So I know that cosine A, is equal to negative 61 over negative 100. So to do my cosine inverse, I'll just do 61 over 100. And I get 52.4 again. So notice, same thing. There is a bit of rounding stuff in here because we're using this angle that I've rounded off, right, in my law of sines, but it's typically not a big deal. I like using law of sines, so that's what I normally use. But you can use law of cosines to find that as well. Okay, I think that's all I've got. At, 18 minutes, this video is probably already a little longer than it needs to be. There's not much with this law of cosines. I didn't go into the derivation of it because it's a little annoying. If you want to, there's tons of places that you can find that. But that's what our law of cosines is. Let me know if you have any questions. Good luck, everybody.